The lecture I'm going to is very connected to the talk of Alessandra, so there are some similar parts, some repetition, but repetition is good also sometimes. I start with some problems showing that in fact tensors are everywhere. And they appear in different forms. And this form, it's good to recognize that they are there, maybe hidden. And so there will be some connection with problems that we are not used to see as tensor problems, but which they are in some way. For instance, the first one, I give you a sequence of values here, some numbers, sigma 1, sigma 0, sigma 1, sigma 2, sigma s. And I ask you, what is the value of sigma n when n is, say, 1 million? Okay, so this is not a very well posed problem because you can say what you want. But if you find a structure in this sequence, then you may be able to use this structure that you have recognized to tell what is sigma 1 million. For instance, the structure we want to detect is this kind of structure where you have some weights and some points to the power n. So we could imagine that each segment, each element here of the sequence is of this form. We are given the first S values, and then we can guess what would be the value for sigma n, assuming this. But here we don't know either the number of terms are here, we don't know the weights, we don't know the point Cn. Here. So, an example. If I give you this sequence, 0, 1, 1, 2, 3, 5, 8, 13, then you recognize the sequence, maybe. What is it? Fibonacci numbers, yes. So the next one you will guess is 21. The sum here, 13, 8. So there is this recurrent relation which exists between the points, between the values. So sigma k plus 2 is equal to sigma k plus sigma k plus 1 plus sigma k. And then if you assume this, you are able to say what is the value of sigma n in a reasonably easy way. You look at this current relation, you associate with polynomial x squared, the characteristic polynomial, x squared minus x minus 1, corresponding to the relation there. You find the roots, you solve this polynomial, compute the roots of this recurrence relation, which are the golden numbers, C1 and C2, and then you are able to find the value of sigma n for n by taking the power of the roots and the weights here, you compute them from the first way. So this is a problem on moment, on a sequence of numbers. Another example where we have a function f, depending, for instance, of the time. This kind of function we have here, which seems to be some cosine and sine function with different frequencies. So we have some oscillation in one, we have some faster one, and some even faster one. So can we guess what is the value? Can we what is this function? Can we decompose it as a sum of combinations of cosine and sine with some frequency ui and weights ai and bi? Or if we look at in terms of exponentials, weighted sum of exponential functions, the weight omega I and the exponential of zeta I times. So from the observation of these functions, from the value of this function, can we deduce this R, which is the number of terms we have here, omega I the weight, and Ci are the frequency. It's also a problem which is, as we see, related to the analysis of moments, of sequence of moments or tensors. Another example is signal processing. We have here Bob, which is speaking, Alice also speaking, Charlie, and so many other people are speaking, emitting some noise or some sound from different locations. And Eve is flying there, listening to what is said and looking. So listening in different places of the place. And she wants to know who are the sources and what they are thinking about. So in fact, we can modelize this problem as some observation Y that Eve is doing. And these observations, they are related to sources of which are both and charging pod. They are related by some H, which is given by the geometry of the position. Right? So the question here is how to recover S sources and how many there are. So and the matrix H. So you want to solve this linear system where you know only Y, and you want to find the system and the solution. So it's a bit impossible or not well posed also, but in fact, it's something that is done in what is called blind identification. If you go not only to the linear part of the problem, but to the higher order moments of measure statistics of this observation. And the technique which is used here is to construct the symmetric tensor that you read from the average or the mean of the observation, the product of observation. So we take here the product yi times yj times yk. We take the mean of this, and this gives you a value, coefficient, which is in fact not depending on the order ijk. So you get, if you collect all these expectations ijk, you get the symmetric tensor, which you represent in this way. So with the value and the variables here, just to say the sequence corresponds to the coefficient of the and from polynomial, if you try to decompose it under some conditions, if you try to decompose this polynomial as a sum of powers of linear form, this is the column of H times the vector of variables to the power V So D here is the number of products present there. In fact, if you do this decomposition, you will recover the colors of each. So symmetric tensors and tensor decomposition are used here to find these sources and identify the number of sources and reduce the geometry. And so here is another example which is more algorithmic to show you that tensors are used in many places or appear in many places. So so you look at the multiplication of matrices. So here we have 2 by 2 matrices, X and Y, and we compute the product by the simple relation. So Z the product is Z prime 1, Z prime 2, with this formula. Nothing complicated. This is, in fact, a formula which is multilinear in X and Y. And so it can be seen as a tensor of multiplication of 2 by 2 matrices, which we see as an element of R4, tensor R4. And we write this tensor in the polynomial form, where we see. You see here we have for Z prime 1, where for Z1, we have the value of the product. And the same for the other. So this is a tensor multilinear polynomials in X, Y, and Z, representing the tensor multiplication of 2 by 2 matrices. And decomposing this tensor in a form which is the product of linear in X times linear in Y times linear in P in a minimal number of ways. So R here in a way which is minimal in the number of terms. We have in fact a way to save computation. For instance, if you do a naive product of 2 by 2 matrices, you will use 8 multiplications, which are given here. These 8 products that we have. But this tensor has a rank which is 7, so you can write it with 7 terms here. And so you say 1 multiplication when you do that. And if you are able to save complete multiplication, you can also improve the complexity of multiplying. So here we say for 2 by 2 matrices, but when you have n by n matrices, you can see them as blocks of 2 by 2. And if you say multiplication for 2 by 2, then you'll be able to say for multiplication of matrices of size n by n. And so the complexity of multiplication of n by n matrices will not be what is classical, which is n cubed, n to the power 3. But here it will be n times the log of 7 in base 2, which is a bit less than 3. So we gain something here. And we can do it for not only for 2 by 2, but for 3 by 3. And maybe gain a lot when we include the terms here. For instance, the 3 by 3 matrices, tensor multiplication. Its rank is 22, which is less than a bit less than 27. And so we gain also multiplication by in the complexity of multiplication of n by n matrices with a log. So it's a log 20. It's a log 20. Log of 22 in base 9. So again, less than 3. And there was and so this technique is employed to consider to answer this open question, which is what is the complexity of multiplication of n by n matrices? So far in algorithm, in the complexity analysis, people use n of omega, where omega is this exponent of linear algebra, which is known to be less than 2.38, and there are some other digits which are known here, and conjecture to be 2. And so this is possibility to reach this exponent 2, which would be quite difficult, like incredible, hard to believe, because here you make the product of n by n matrices which have n square entries in the same complexity as their organization. N square seems to be impossible, but it's however it's conjecture, and it's the techniques to decrease this exponent are based on the genetic of tensor, and in fact there will be a talk by Landsberg, this week on this topic. So there are tensors are even problems. I will so describe them, their shape, how we see them, how we manipulate them now. We consider here coefficients which are real or complex or rational number, but it could be also numbers in finite field. But our discussion, our representation here will be related to coefficient fields which are like the real field or the complex number. So multilinear tensor, they are usually represented as a multi-dimensional array where your entries T, I1, I2, IL, they are in fact the coefficients in the basis of the tensor product of vector spaces K and 1 tensor K. We can see them as polynomials, just as take the coefficients here, and the basis here will then variable T. So x1, I1 is gone. So it's a multilinear polynomial in the variables x, ij. And the dimension of the space is the product of the dimension of n1 times n2 times nl. Symmetric tensors, what are they? They are elements, we can see them as tensors with some symmetry. So the symmetry which leave invariant the coefficient when you permute in. So Ti to 1, I to 2, I to I2. It's the same as Ti 1, Ti permute and define the same value. And so you can represent this coefficient Ti1, Ti2, Tid by putting all it has the same value as when you put all the 1 at the beginning, the alpha 1, 1, then all the after alpha 2, and so on, alpha n. So this is also a coefficient T alpha 1, alpha n. And here the alpha, they are the number of 1 plus the number of 2 plus the number of n is equal to d, which is the total index. So we represent this in a multi-index way, T alpha 1, T alpha 2, T alpha n, with the sum or the degree of alpha, which is equal to. Again, we can see this as a polynomial in variables x1, xn. Instead of taking x, say, I1, 1, we take the same variable, so xi1 is L, and we take the sum of this, which gives the polynomial P alpha. So D alpha is a binomial coefficient alpha factorial, so what is it? D factorial over alpha 1 factorial and alpha n factorial. We use a multi-index notation. And so the symmetric tensor is also a polynomial which is in the variables x 1, xn, which is homogeneous for degree. Okay, we see. In the variables x1, xn, and so homogeneous in the variables of degree d, which is the order of the one. Okay, what else to say? It's a space denoted Sn d, n is the number of variables, and d is the order. Its dimension is this binomial coefficient n minus 1, 2. So the number of monomials of degree d in n variables. Okay, just to show that these are explicit objects that we can compute with. I show you some sessions in some computation done in Julia. Tensors exist by default in Julia. So there are multi-arrays, or there are solved arrays with different orders. So here we construct this tensor, which entries are the sum of the indices. So this is the T, the multilinear tensor, where we have here first matrix corresponding to the first slide, which is 0, 1, 2, 1, 3, 4. And then there is a second matrix representing the slice, this one, and the sum. And we can see this as a polynomial with the variables x0, x1, y0, y1, y2, 0, 1, 2, just by taking the sum of these indices p I j k times the corresponding variable. It gives this, which is another representation of the same object. Okay, so one can see tensor, or let's say the equivalence between this representation and first. Maybe this is more fact, and see more. We will prefer to use this representation. When we can remark that this tensor T is symmetric, because when you switch the indices I, j, k, you permute them, the value the Aljk is not changing because it's a sum. So it's a symmetric tensor. And so what is a polynomial we get from this tensor? We just make the same construction, but except that we use only the variable x and not y and z. So y becomes equal to x and z also. So we get this polynomial, which is the sum of Aljk x I plus 1 j 1 k plus 1, and this gives this polynomial where we see we have some binomial coefficients which appear 3 here and 3 times 2 here. So we prefer this form, and I prefer this form. Deal with present things when tensors are given in this form. So one of the interesting feature we have on symmetric polynomials, homogeneous polynomial, is this apolar product, which has many nice properties. So given polynomials, so f and f prime are polynomials of degree d. So this is a compact representation. We have coefficients f alpha. Alpha is a multi-index. So alpha 1, alpha n. The sum of the alpha is d. So x alpha is x1 alpha 1, xn alpha n. We have these two elements, these two homogeneous polynomials living in S and D. We define the apolar product in degree d of f and f prime as a sum of the binomial coefficient d alpha inverse times the product of the coefficient f alpha, f prime alpha. So usually, if you like say, the Euclidean product, you will not put this binomial coefficient. But here, it's really something which makes things nice and in fact invariant for the action of so what is nice with this product is that this apolar product is when you take the apolar product of the form f. So yes, I say a polynomial homogeneous degree d. I also call it a form. That's also what you can see in the literature. So the form of degree d times the apolar product with u scalar x. So this is u is a vector, x is the variable vector. So this is sum of ui time to the power b. This is the evaluation of f at the point u, u1, un. So taking the apolar product with the power of the linear form is like evaluating it at the that's already a nice problem. Another one, which is you take this power of u scalar x, the d minus 1, and you take another vector of v scalar dot product with x. This acts as a derivation. So it's you derive in the direction of v, the form f, you evaluate at u, and you divide by v, which is the vector of this apolar product is like a derivation, acting also as a derivation in the direction d, except that you have up to this scaling factor. And so we have here, repeat this for several vectors, v1 and k, times u x to the d minus k. It's a repetition of derivation with some coefficient here, the number of derivation per q. Again, the apolar product like with product of linear forms act as derivation. And so you can use this to get what corresponds to the Taylor expansion in the homogeneous setting. So you have here a basis U1, U2, UN of Kn, which is assumed to be orthogonal. Then the Euclidean. And so with this, and take the expansion in the coordinates that stated, and get the representation of your polynomial form f in this way. So it's here a product of u1 times x to the power alpha 1, and then you do x alpha 2 up to when x alpha n times derivation at the vectors, which are u1, un. So these are coordinates which are orthogonal to the vector u1. So here we are in a projective setting. And somehow you can look at this as you choose the direction u1, you have an orthogonal space. And then in this space you choose this orthogonal vectors of normal basis u2, un, and look at the expansion, the Taylor expansion in this coordinate, which is that, and which corresponds to the diagonal product. So now you have this expansion in terms of powers of y and x, times the polar product of f with this So yes, we have the binomial coefficient which is here, and somehow it's showing that this, if we take the square root of binomial coefficient, they form and multiply by this monomial with the ui x, this form an orthogonal basis of Sn, the form of the grid, for this apolar product. Okay.
So maybe you were just too quick for me. So in the So in the Taylor expansion, the first displayed formula, there's only f of u1 at the end.
Yes.
So why u1 as this preference appearance with respect to, I mean, I don't see any. Could I write the same thing for fu2 and then swapping the partials of? Okay. It's just a choice. You did it.
It's a choice.
Okay.
And in fact, it's just because here you see you virtual u as a special direction, or vector, unit vector, and we look at what are the products. So we have a power of u. We want to somehow to represent in terms of powers of u times u1 times. And this representation is explicit here by when we have to take the derivative for with respect to two vectors to get this representation in terms of u1 times. And this representation is unique because here we have an orthogonal vector. Okay. Another property is that it allows to define duality, a natural duality on the polynomial. So duality here is where you are given some vector, you look at also some vector space, you look at the vector space of linear forms on this classical duality. So when we are given an element F in S and D, and we can look at, and given this polar product, we can define a dual element, which is living in the dual of S and D. So it's a linear form from S and D to K. So it's a linear functional living here in the dual. And how you define it? You define it in a very natural way. As soon as you have a linear product, you define the linear form, which given vector P in the S and D computes the apolar product of F with P. This is a dual element, linear functional, living in S and D dual. We have a bit more than just vector space duality, because polynomials, we can make products. So we have a way to multiply the polynomial of the pk with the polynomial of the bt minus k, and we obtain an homogeneous polynomial of the bt. So we have also, in this way, the transpose of the product, which acts on the dual. So this is denoted by a star here. So Q is the polynomial of the which should be H. H is a polynomial of the Vk, and we define H times F star. So this is a linear functional living in the dual of S and D minus K. So polynomials, homogeneous polynomial of the D minus. And how we define this Q times F star? It's the apolar product of, so the multiplication, we multiply P by H and we apply F. So it's a composition of the multiplication by H with F star. So this defines an element which is living in S and D minus K dual in a very natural way. That's as soon as you have a product space, look at the dual, you have the transpose product, which exists and defined naturally in this way. So this is not magic, it's just by default. Okay, and so with this language, when we have a form which is represented as some weighted sum omega I times C I x to the p, this power of linear forms, if you remember, it acts as the evaluation at the point. So this means the same thing as it's equivalent to saying that F star, our linear functional, is a weighted sum of evaluation at the point. So I denote E of C, the evaluation, which is a linear functional, given a form P, compute the value of P at the. We rephrase this definition and the definition and this property here in this way. We say that F star is a weighted sum of evaluation. So we look in the grid. So this is a restriction in the grid of on the polynomial of the grid. And if we use the language of measures, so this is also called the Dirac measure. We see the connection with measures soon. It corresponds to the Dirac measure at the point.
Sorry, once again on the notation. The omega i's are scalars. And like this round bracket
And here I mean PI dot product with X. So this is the sum of I, J, X, J. So,
Okay.
So what is C X? This is sum I X. Here.
Okay.
So I have a point here, and here I have a vector of variable.
Okay.
Belonging to Kn, and this is equal to 1. Okay. So
Now, the square bracket exponent notation.
Yeah.
A star is defined on an SND, right? So what do you want to
so
restrict?
F star is a yes,
It's already defined there. So what do you want to restrict?
it's some abuse of notation because yes, in fact we don't need it. But I introduce this notation to say we look at it in the preview.
And your SD of Kn, this is SND.
Yes, this is
SND.
SND.
I thought that the square bracket around D means like the power series.
Yes, so we will see the connection with power series, but it's also a truncation of power series or restriction on the subspace.
Yeah, but that's not needed. I mean,
No.
that's where it's defined.
No,
but
but
the bracket, I mean, the fact that you
Yeah.
don't use the coefficients is
I agree. We could forget that. But I want
no,
to-
because if you don't write it, then it's
Because
like
I
the sum
define-
of linear forms. You
I
really want to
define
raise
this-
the power.
I defined this already on S. So I could get that. But this is the so maybe yes, it should be removed. This
No,
is
sorry.
confusing.
So then I don't understand. Omega I is easy I. It's still a linear form. It's not a
Yes,
form of
this
degree
is-
D.
Omega I times multiply by the evaluation at Ci, which is a linear function.
Yes. That's F star. Sorry. Got it.
Yeah.
Thanks.
F star here is the
I got
element of the-
So I agree that
and
it's
this
really not neat.
means we look at this specifically in the grid.
Got it.
So because the evaluation you can define it for any. But yes, maybe it's a bit confusing, but to be precise, we look at restriction on the polynomial. Okay, so now making the connection between sequences of numbers, series, duality, tensors. So we are dealing with the same kind of objects, which are very related. And so I want to explain it a bit. So we are now in 1D, one dimension, one variable. We look at a sequence of values, sigma 1, sigma 2, sigma 0, sigma 1, sigma 2, and so on. So these are sequence of numbers. So they are elements in K to the N dimension number. Well, these are many values. So if we want to deal with, to treat this as a unique object, sometimes we can look at it as a formal power series just by introducing a formal variable y and say we take the sum, the infinite sum of sigma k y k. It's a formal power series. That is an element of this K of the double bracket one. It's so the object that Algebra like to introduce, but we are not taking care of any convergence of the series, any property or any analytic property. Just a formal part. So this is one choice, but sometimes it could be interesting to say this is a formal power series in variable C, but we take instead of yk, we take ck over k factorial. And you will see why soon, because it's related to exponential. So we have now our linear functionals on polynomials. So here, k of x is the ring of polynomials in the variable x coefficient in k, and these are the linear maps from k of x to k, the dual. So we can make, we have a bijection between all these objects, so k to the n, the formal power series in 1 over d, and the linear functionals in on k of x, simply by, you see, by the linear functionals, you are given this polynomial, which is the sum of pi xi, so a finite sum. We can evaluate the linear functional on P by taking the sum of lambda I pi, where lambda I are the value of lambda on the xi, or the sequence or the coefficients of the formal form. This is a way to see sequences, formal power series, and linear functionals in the same way. So as the same object. And here again, we have since we can multiply polynomials, we have also the possibility to multiply a polynomial with the linear functional. We define P star lambda as the linear functional which maps the Q. So we multiply by P and then we apply. So this is like the transpose multiplication by P, which is composing with the multiplication first and applying the linear functional. Now, in this different representation, what is the effect of the multiplication by x? Okay. So x times sigma y is, in fact, you can check. This is maybe an exercise. You replace x by y inverse. Take the product of the y inverse with the formal power series in y, and then keep the positive exponent. So this is the if you use the variable z with the k factorial, x times sigma of z is this series. So sigma k is k minus 1 k minus 1 factorial. And you see that this is nothing else than the derivation with respect to z of the series. So in this formalism, the multiplication by x is like the derivation. So we have a duality between multiplication and derivation in the dual. The same here. So when we multiply by a polynomial theory times a series or a linear functional or a sequence, in the y, we replace y by y inverse, p of y inverse times this series, and keep the positive exponent. And there, it's a derivation. We replace the variable x by the derivation with respect to z, and we apply it. So this is a polynomial differential a differential polynomial applied to sigma, which is this one.
So sorry, again on the notation, the first partial is partial of x. The second partial is just, I mean, all possible partials.
Yeah, this,
This is like partial of x, partial of y. It's like a
no,
vector.
this is a partial with respect to the variable is
I think there is a type which should be Z, the symbol on the left, right? Z composed with sigma of Z, not X.
Ah, yes, okay. So it's partial with respect to z.
With no X.
What is x on the right? You have x on the left, but you don't have x on the right. Yes.
Yeah, so what you do is P of x, you replace the variable x by the derivation with respect to z. And you multiply this polynomial derivation.
How do you choose z?
Is the variable that we use.
But Bernard, it's not X, it's Z, right? Variable.
I'm
No, no,
confused.
so our format our series are variables y or
So the X is the element in the two bring it on. So this is why the accent differentiation.
x. Yes, x is our variable in the primal. And the duals, they are represented with the variable y or z. And now we do the product of the polynomial in the primal with an element in the dual. And the product of this in the primal times the dual is like replacing the primal variable by a differential and applying it to the set. So here, yes, we have
Bernard, how many Z do you have? Just one.
here one z, and one y.
But then your partial derivative is just derivative.
Yeah. Yeah, but the partial. So, for instance, suppose you have our polynomial is P of x is equal to x squared minus 6. So what will be the so P of delta of t? This will be delta of z squared minus delta of t. This is a differential polynomial with respect to, and we apply it to the setting. So we apply this on. Okay, so it will be the computation with this. So here the sum of sigma k t to the k minus 2 over k minus factorial minus. But what has to be seen is that it is acting as a derivation. So we have some algebra of derivation, but we have here polynomial acting on the thing. So just to see that they are not so, it's a convenient way to write things. So, for instance, when we look at the linear functional, which is computing a specific coefficient in a polynomial. So we fix a I here, and we look at the coefficient of each side. So what is this? Linear functional? How will you represent it? Well, we can represent it the y just as y to the I. Y I are dual to the product. So it's just yi, which is computing the coefficient. But in the zi basis, it will be 1 over I factorial times CI. So we have here yk, which is dual the monomial vectors, and ck over k factorial, which is the same, the dual. If we look at the product on the of x with y I, this is like y I minus, except if I is 1, is 0, where this is the product here of x with di, this is I di. Now, more interesting, when we look at the evaluation, which is so the evaluation at CI. So by definition, this linear, the series associated to it is a linear functional is the sum of the value at the monomial times the monomial yk. So it is zeta k yk, and we recognize the expansion of 1 over 1 minus y in this ring. We do the same with the variable z. So we have zeta k over k factorial. And we recognize here the exponential of zeta. And so the evaluation corresponds to the exponential in this format. So since you have seen already, for instance, when you have in measures, when you have Diracs, and then you Fourier transform, you get some. So it's related. So you see the nice thing is that when you have the z variable, you have exponential, so compact foundation, and then the x times the exponential of zeta z is like the derivation with respect to z. So you find zeta times exponential. And see that here, this exponential or this evaluation is an eigenvector of the multiplication by. If we look at the multiplication by operator, this is an eigenfunction. Okay, we will use that later. We do the same exercise with multi-indices. So now we are in dimension n. We have variables x1, xn. We have multi-index sequences alpha. Alpha is in n to the n. So it's an element of k to the n to the n. Alpha is also multi-index. The sigma are sometimes called the moment sequence when these are coming from measures of pseudo moment sequence. So they are simply values indexed by this alpha, where alpha is also the exponent of monom, of a monom. Same thing, we can look at this as formal power series. So sigma of y will be the sum of sigma alpha y alpha, just to have the representation in one series. Or if you want the generating series or the sequence, the same choice with z, we can use z alpha over alpha factorial also instead of y alpha. Linear functionals, so they are given by the value, they are defined as soon as we know the value of the linear functional on the monomials. So this is a sequence to do. And so even the index sequence or formal power series, we define the unique. This is in correspondence with the linear functional defined this way. Again, y alpha you add to the monomial vector, or z alpha we are at x. And we have the same property for.
And also a moment sequence is just a sequence of vectors.
Of a value.
Of
Values. So these are numbers.
but alpha is in n to the n.
Yes. These
So
are
it's a
values.
sequence
And x. No, the alpha is a vector. The sigma alpha is a value. So we have like monomials with exponents, and for each exponent we have a value. And this is the moment sequence.
So the sigma are like put as the coefficient of polynomials, not just for any.
They are coefficients of, yes, they could be coefficients of series here. Or,
No, the question is, they have to be the coefficients of your polynomial or your series, or they're just you define, how do you define moment sequence?
an element in k to the n.
Ah, okay.
So a sequence of values.
Okay.
Indexed by multi-index. And so this we see it as formal for a series or linear functional. The same object. Linear functionals defined on the, say, the polynomials. Now we don't restrict the degree, we take all the polynomials and variables. Yeah. Okay, so that's about formalism. And now we can, yes, we continue a bit with the formalism. So now we can look at this sequence truncated in some degree, or the series truncated. And we define, so Rn is a ring of polynomials in the variable on cell. Rnb, now it's R dot S, is a vector space of polynomials in degree less than d, so spanned by the monomials of degree less than d. And so we can look at truncated moment sequences. Alpha with alpha is of degree less than d. And we can look at what is called here truncated linear functionals. They are linear functionals defined on polynomials of the degree of d. They are the dual of R and truncated series. When we are given the series in K of Y or in K of Z, we define, actually it's not here instead of typo, we define the series truncated in degree D as the series where the exponents are taken up to the. So this is the same as this, and the same way to, different ways to look at the same object. Different representation. So it's about representation. It's but mathematically there are this linear functional over the space of polynomials up to the group. So yes, we also have a, so for a P in the degree of degree K and the linear functional up to the degree P, we define P star lambda as a linear functional in degree less than P minus K by, as we have seen before, so it's the composition of multiplication by P. Okay. Now, so we have talked here about sequences, linear functionals, series. What about moments? How can we make the connection with moments? So, given symmetric polynomial or symmetric tensor of order D, which is written in this way. So here we have f alpha, the coefficient. And now I write the variable here, they are starting from 0. So it's 0, alpha 0, 1 alpha 1, 7, 10. Alpha, the sum of alpha I, 0 plus alpha 1, dot equal B, so WD, the form is n plus 1 variables of WD. We can associate with an element in the dual of polynomials in n variables and W less than B in a very natural way. This is explicit expression. So we have f alpha d another coefficient d alpha inverse times this y 1 alpha 1 y n alpha. And what is the property we find? So this is f change. The f star we have seen which associated to a given tensor or form this element in the dual WP for n plus 1 variables is in fact the composition of f change with this substitution, which replaces x0 by 1. So it's the effect of going from, say, projective context, projective geometry, to a fine. So here we replace the variable by 1. We get a polynomial of degree less than b divided by itself. And the corresponding form associated to f on this ring in place here is f. And how we go from the fine setting the homogeneous to the projective or the homogeneous setting, we do homogenization. We have this relation to f change is f star composed with the homogenization, which is a linear map taking a polynomial of the less and homogenization in the BD and variables x0, x0. Okay. So here we have an homogeneous polynomial of the BD, a tensor, a symmetric tensor. It's the same, or it's identified with a linear functional in space, individual. That is a truncated sequence of moments up to the BD, or a formal power series truncated BD or polynomial in this dual variable. Okay, so using this, we have, in fact, we are dealing with the same objects, tensors, sequence of the domain, formal power series. And just to show you that this is not this is effective. Here are some examples in Julia again. So we are given this variables x0, x1, x2, the degree is 3, and we look at this form, which is the sum of the two powers of x0 to the b and x0 to 1 minus 2. And it corresponds to this polynomial. On the here, there are some here. Now we want to see what is the dual of this element in the homogeneous setting. So there is a function in this package which is divide series, which takes the dual. So simply dividing by the binomial coefficient. Something very difficult. So the dual of f in the group B is linear functional. So we have to treat it as the dual variables y, I, they are called here p, x1. So the trick here is that if we have variables ABC, then the dual variables will be A, B, B. So that's the notation. Bx2 is the dual, the primal.
So F star is homogeneous.
Yeah, F star is homogeneous.
But in your previous slide, it was not. In the previous slide.
Yes, it was, but F change was not homogeneous.
No, F star is F is the composition of F with the I that is the
Homogenization.
Yes.
Yeah, but they are F star is dealing of the dual from the
But how should I read it? So F star is equal to F chat, and then you compose with that.
yes, this
Iota that
substitution.
Yeah, but this is a non-homogenization. So as it is there, is non-homogeneous.
Yeah, but, okay. But this is non-homogeneous. It's a dehomogenization, and this is the form defined on the affine polynomial.
So F star there is not homogeneous.
F star is homogeneous. It's defined on the dual on the homogeneous polynomial. I don't know.
Homogeneous. And then star was the
Yeah, as it is written here, it's the dehomogenization of F chat.
Okay, there is a mistake here. Alpha should be so alpha 1 plus alpha 2 less than. Okay. Yes.
So I0 is not the dehomogenization, but is the homogenization.
I0, you take an homogeneous polynomial, you make it affine.
So F star is
So-
fine. I think it's
F
changed.
star is non-homogeneous, so it is fine there.
The I0 should be on the right, the HDX should be on the left.
Okay, then it's fine, but it's not what's equal to. Yeah, it's Orialis is that. You have to apply this.
No. So you start with so this is a map where you apply I0 and then you apply the change. Okay? So it's a map going from Sn plus 1b, then you apply S change, which is going from, you arrive in NB, and then you apply F change, which arrive in it's defined.
But you apply F to something that's fine. So you've got like a.
Can we make a baby example?
Yeah, so that's next thing. Please F star.
Yeah, but I
Okay.
don't see. I see
So
that. Check, where's F check?
Change is the next step. It's here. So, yeah. So let me just discuss this. We have a star defined as with the polar product. This is the dual representation. We have d x0 point. So dual to the variable. Now we do the substitution f, we replace x0 by 1.
Yeah, so it's our real set. So
So
we
this is
apply
the-
I0 on F star.
So this is the affine polynomial, which is this one. Just you replace 0 by 1. You know,
Yeah, so isn't that the comment that you got before?
Yeah, no, but it's right because it's taking the polar.
So that star is already the dual.
but it's a map. So look at it as a map and see from which place it's going. So now you take the dual of this model.
Okay, sorry, can you go back to the previous functions with the fact that you have -2 coefficient and +6, and then in the Lagrange you have -2 and then +2.
Yes, so they are not ordered in the same way, but this coefficient here corresponds. Yes, this monomial.
It's not F star.
But they are not ordered in the same way. But this is just a substitution. So 3, okay, 3 you see is when you replace this term is 0 by 1. So this is just substitution by 0 by 1, and then this is FH. So we take the small f, fine, and take the dual. And it gives this linear functional, which is acting on polynomials in x1, x2, up to degree no x0. And we have just divided by the binomial position. Okay, so it's what's happened when you go from, let's say, when you go from an homogeneous polynomial to an affine polynomial by substituting variable 0, then you look at the dual. What you get is this element leaving in k of x1, x2, which is the dual of polynomials up to the root. And now we can apply this linear functional on x1. So S applied on x1, we get 2. But yes, so 2. This is the dual basis of polynomial basis. So x1 we have here, and the dual is here. The coefficient is 2. We look at x2 times S with the definition we have seen. So this is S applied to x2 times something. So you see that it's like multiplying by the inverse of x2, of dx2, and keeping the positive exponent. So if we multiply by the inverse here, we will get a negative exponent there. There it will be 1. Get this minus 2. This x2 will disappear. This one will become x2. And we get this one, and so on. It's like the inverse. But if you multiply by the inverse of the variable, and you keep the exponent. And now we can apply this S2, which is here, x2 times S on the polynomial of degree 2. And we get x1, so we apply it to x1 square plus x2 square. So we look x2 square, we have a minus 2. X1 square, we have here minus 2. We take the sum, we get minus 2. Okay, so basically, okay. So I think I will and it's short in time. So I think I will stop here. We'll continue. Okay, so if you have more questions. So, the idea is that this duality allows to see the same way problems of decomposition of tensor and moment sequences, which are, for instance, appearing in polynomial optimization when you want to recover the minimizer from the moment sequence. Okay, so we stop here. Tomorrow we'll have the pattern in the reading, which is defined there. So level at the entrance